Hi, I'm Shanawaz. Let us start this lecture with the basis theorem. And the statement of this theorem is like this. So it states that every finite abelian group G is direct sum of primary scalar groups. So every finite abelian group is direct sum of primary scalar groups. So let us prove this theorem. So now let us consider a finite abelian group G. So let G be over a finite abelian group. So we may assume G is P primary for some prime P. This is because of primary decomposition theorem, which states that every abelian group G is direct sum of its P primary abelian groups, P primary components I mean. So we may assume G is P primary and this is for some prime P. And let us use induction on D of G. So we use induction on D of G. Note that since G is P primary, so then D of G is actually dimension of G mod PG over a finite field with P elements. So we are going to use induction on DG. Now for the base step, so if DG is equal to 1, then we proved earlier that if DG is equal to 1 if and only if G is a pure cyclic group. I mean if G is a non-zero cyclic group if and only if G is a finite P primary abelian group with DG is equal to 1. So if DG is equal to 1, then obviously G is a non-zero cyclic group. This is actually a result which we have done earlier. So then clearly G is a non-zero cyclic group. Now assume the result is true for all finite abelian groups, say H, such that D of H is less than D of G. Assume that the result is true this is true for all finite abelian groups abelian subgroups. I mean abelian groups say H such that d of H is less than d of G. So this is our assumption. Now we are going to prove the result is true for dg as well. Now G being a finite p primary abelian group, so it must have a non-zero pure cyclic subgroup. This is again a result which we have done earlier. So G being a finite p primary abelian group, so it must have a non-zero cyclic group. So non-zero pure cyclic subgroup. Say S. So let us note this subgroup by S. Then again we know that, so then d of G is actually equal to d of S plus d of G mod S. This is again a result which has been proved in previous lectures. Now S being cyclic, so this d of S must be equal to 1. So this is, or d of G is 1 plus d of G mod S, or so let us write, so this implies d of G mod S is less than d of G. Therefore by induction hypothesis result is true for G mod S as well, and hence by induction hypothesis this G mod S is direct sum of, so this G mod S is direct sum of x1 bar plus direct sum x2 bar plus so on plus xn bar, or let us write this xq bar. So this result is true for G mod S, which implies this G mod S is direct sum of it is cyclic subgroups. Note that these xi bars are, so where xi bar is actually xi plus S. So actually these are the cosets of S for all I. So let us pick any element G in G. So let G belongs to G, be any element. Let G bar be its coset in G, coset of S in G, i.e. let G bar be equal to G plus S, i.e. the coset of S determined by this element G. So let this G bar have order p to the power L. Note that G being p primary, G mod S is p primary as well. So that is why its order must be power of some power of this prime p. So order this G bar has, so that this G bar has order p power L in this group G mod S. So let us lift this element. So what we want to do, we want to lift this element. So by lifting we mean, so we know we have a natural map G from G mod S. This is a natural map, canonical map. So it takes an element A to its coset in G mod S. So actually we want to lift, so this is again this projection map pi, this is pi. So we want to lift this map such that, so if we have G here in this G mod S, which goes to G bar, which is same as G plus S, we want to lift this element again in G such that, so this G goes to some Z in G such that its order of Z is same as order of G bar. So we claim, so this is our claim, that there is some lifting, there is a lifting Z in G, that is this Z plus S is same as G bar, which is same as G plus S. So actually we have this G mod G here and this G mod S here, and this is this G. This is the natural canonical map pi pi, and we have some map here from G to G. Now what this pi does, it takes an element G and it maps to G plus S, which is same as G bar. Again this map takes some Z to this G bar, so this is equal to G bar, and this map which takes this Z G to this Z, so it takes this G and it maps to this Z. Now what is special about this Z? It is that order of Z is same as order of G bar, so such that order of Z is equal to order of G bar. So this is our claim, and we have to prove this claim, that it is always possible to lift some G in G. So we can lift this G, I mean we can lift this projection map such that this G plus S and this Z have same order. So let order of G be equal to p power n. So order of G is called p power n. Now note here, so this G goes to G plus S, which is same as pi of G, obviously, which is G bar I mean. So obviously order of G bar divides the order of G. This is the basic property of a homomorphism. So if F is a homomorphism from G to G prime, and where A goes to F of A, then order of F of A divides the order of A. So here this G goes to G bar. So order of G bar, must divide order of G. Now order of G bar is p power L and its order of G is p power n. So p power L must divide p power n. This means that this n must be bigger or equal to L. So let order of G is equal to p power n. Then n is bigger or equal to L. Now but p power L of G, p power L of G is, so if we look at this element p power L of G times S, so this is the coset of S in G, so this is same as G plus S, G plus, so this is same as p power L of G plus S. The reason being, so this is same as G plus so on plus G plus S. This is p power L times. So we can write this element as same as G plus S plus so on plus G plus S, p power L times. So this is p power L G plus S, which is same as p power L, and this G plus S is G bar. Now we have assumed at the beginning that the order of this G bar is p to the power L here, so this is 0 here. So this means this p power L G is in S. So this is equal to 0. So when this is equal to, I mean 0 bar, so when this is equal to 0 bar, which is same as 0 plus S, that means this p power L and G, this is an element of S, so which implies p power L G, sorry, p power L G is an element of S. So if this is an element of S, then there must exist some element S prime in S such that p power L G is S prime. So therefore there exists some S prime in S such that p power L is G is this S prime. But S is pure subgroup. So let us denote this by S. So this is, there must exist some S in S such that p power L G is S. But it is given that this S is pure subgroup. But purity of S implies that there exists some S prime in S such that p power l g is p power l s prime. So we are done halfway. Now let us take, so this is our claim here. So we have claimed that we have a z in G such that order of z is same as order of G bar. Now let us define that z. So if we define z to be equal to G minus S prime, then this is G plus capital S, this is G minus S prime plus S. So this is same as, now this S prime is an S, so this is same as G plus S. So this Z plus S is same as G plus S. Also, now we have to prove order of Z is same as order of this element, I mean order of G bar. Also, if order of Z is equal to p power, first let us do this thing. So let us erase. So if we define, this Z to be equal to G minus S prime, then p power L of Z, which is equal to p power L of G minus S prime, which is same as p power L G minus p power L S prime. So which is equal to 0, because this p power Lg is equal to p power L S prime, so their difference is 0. So that means that is, so if a power m is the identity and order of a is equal to suppose n, then that means this n is lesser or equal to m, because n is by definition of order, this n is the least positive integer such that a power n is e. So this n must be less or equal to m. So we have proved that p power L of Z is 0. So that means i.e. Order of Z must be less or equal to p to the power L, because p to the power L of Z is 0. So it is order must be less or equal to this number. Again, this Z plus S, which is same as G minus S prime plus S. Now this S prime is absorbed in S, so this is same as G plus S. Again, this is equal to this, and knowing the fact this Z goes to Z plus S under the projection map, which is same as G plus S. So order of G plus S must divide order of Z, i.e. now order of G plus S is, now G plus S is G bar, so its order is p power L, and order of Z, so this is this thing. So on comparing these two things, we have Therefore we have order of z is same as order of g bar, which is p power l. So what we have done so far is that, so given any element, so if we have this natural map G to G mod S, which is the natural map pi, so if G goes to G plus S, it is always possible to find an alternative element, say Z instead of G, such that this Z goes to Z plus H S, which is same as G plus S, and order of Z is same as order of G plus S. So otherwise order of G plus S always what is order of G, but it is always possible to find an alternative element of, I mean an alternative for G, such that order of Z and order of G plus S are equal. So it is always possible to lift such element such that their order is same. Now let us do this thing. So for each I, choose a lifting say Zi in G, such that order of Zi is same as order of Xi bar. Now let us define this group. So define T to be the cyclic group generated by these elements Z1, Z2, so on, ZQ. Then clearly, now what is same between T and G mod S? So this G mod S is generated, is actually the direct sum of these Xi's, where this I runs from 1 to Q, and this T is the subgroup generated by these Zi's, ZQ's, where order of each Xi is equal to the order of Zi. So this means this T and this G mod S, they are isomorphic. So clearly G mod S is isomorphic to T. Therefore this G is equal to the direct sum of S and T. So if this is true, i.e. G is S plus T. Now it remains to prove, so sorry, so this means, therefore, so since we have seen earlier that G is actually S plus G mod S. Now this G mod S is isomorphic to T, so this G is sum of S and T. Therefore this G is S plus T. Now to see G is actually direct sum of these two subgroups, it suffices to prove their intersection is singleton. It suffices to prove S intersection T is trivial. So it is trivial subgroup. So let us consider an element Y in their intersection. Now since Y is in T, since this y is in T, and T being a sub group of G generated by these elements, we have y is actually sum of these linear combination of these zi's. So this is mi zi. This I goes from 1 to q. Where mi's are in z, I mean they are integers for all I. Now since y bar, this is in G mod S, where G mod S is direct sum of these cyclic subgroups, we note that we have, so this y bar is actually sum of, say, mi prime I xi bar, where this I runs from 1 to q. But this y bar is actually 0 bar in G mod S, and G mod S being direct sum of these subgroups x1 bar plus so on plus xn bar, we conclude that this expression is unique. So we conclude that this sum, that this mi xi bar, mi prime xi bar is equal to mi zi bar. Zi is actually 0 for all I. Now if this is the case, this means, so this is zi bar, therefore this mi zi is equal to 0 for all I, hence y is equal to 0. Therefore this G is direct sum of S and T, but this D being additive over direct sum, we have also D of G is same as D of S direct sum T. Now this D is additive over this direct sum, so this implies this is D of S plus D of T. Now D of S is 1 plus D of T, so that this D of T is less than D of G, and hence T is direct sum of cyclic groups, and hence T is direct sum of cyclic groups. So if T is direct sum of cyclic groups, put that combination over here, we are done. So this was the basis theorem.